right, welcome to section 5.1, where we're going to solve trigonometric equations. Today's essential question is how we can find all of the solutions to a trigonometric equation, and that word all is going to be very particular, as we're going to learn here in just a minute. All right, so first off, ask yourself how many solutions there are to the equation sine of x equals 1/2. In other words, how many times is sine of x going to be equal to 1/2? All right, there's actually going to be an infinite number of solutions. And we're going to justify it in a couple of ways, and then we're going to talk today about how we can actually write all infinite of those answers out. So first off, justifying that there's an infinite number of solutions. One way we can justify it is by the graph of sine of x. We should know that the graph of sine of x starts at 0 and goes up and down and up and down and up and down, and it just never stops. It keeps going up and down forever, right? Well, it goes up to a value of 1 and down to a value of -1. And if I asked how many times is this graph going to be equal to a value of 1/2, well, it's going to be equal to 1/2 an infinite number of times. Right there, and again right there, and again right there, and there, and there, and there, on over to infinity, and backwards too, all of these ones. So there are an infinite number of values I could put in for x, so that sine of x equals 1/2. All right, we can also justify using the unit circle. Hold on one second. All right, here I've got the unit circle, and on the unit circle, we know as our angle goes around, it has different values. We know that sine it's a y value, so I've got a y value of 1/2 right here, when the y value is 1/2, and again right there, when the y value is 1/2. And with a unit circle, it can go around and around and around all forever, right? So every time I go around and hit here, there's a sine equal to 1/2, and then there, sine equal to 1/2, and it comes around again. So using either the unit circle or the graph of sine, we can see that there's an infinite number of angles that have a sine of 1/2. So today, what we're going to learn how to do is actually how to find those infinite solutions. And we're going to start right now. Oh, before I forget, there is a handout. There's a handout that has both the unit circle and some common trig values on it. You can use that unit circle and the common trig values as we move forward. It's things you probably don't need to use because we should know what the unit circle looks like at this point. But if you want to, they'll be available to you. You should find it in the folder in Schoology. All right, real quick question. What's the period of sine of x and cosine of x? Hopefully you remember. The period of sine and cosine is 2 pi. Those values repeat every 2 pi units because there are 2 pi radians in a circle. All right, so here's our first equation. We're going to solve the equation 2 times a cosine of x plus 1 equals 0. I've got a picture of the unit circle over here that can help us out. And we'll just go ahead and solve it. You start off by solving this just like you'd solve anything else. I want to try to get x by itself. So to get rid of that plus 1, we can subtract 1 from both sides. 2 cosine of x would be -1. I could divide both sides by 2. Cosine of x would be -1/2. And there's where I'm going to pause and we're going to do something a little different. Now, earlier you might have said, hey, I know how to get rid of cosine. I'm going to do the cosine inverse of both sides, because cosine inverse and cosine get rid of each other. It totally works. The only problem is cosine inverse is only going to give you one answer, and I've got an infinite number of answers I need to get to. So if I tried cosine inverse on my calculator, I would get out an answer of 120 degrees, which is the same as 2 pi over 3 radians, and it would be this one right here. But that's only one answer. Cosine actually there's an infinite number of values of x that could work. So instead of just using my calculator, I'm going to use the unit circle. I know cosine is equal to the x value. In this case, an x value of -1/2. Well, that happens right here at 2 pi over 3 radians. It also happens on the unit circle right there at 4 pi over 3 radians. So there's two answers already here. I've got one angle like that. So x could be 2 pi over 3. Or I've got an angle like that. So x could also be 4 pi over 3. But we had mentioned there's actually an infinite number of solutions. And those infinite number of solutions has to do with the fact that we can go around and land there again, and around and land there again, and around and land there again. Well, every time we go around, that's 2 pi radians more. So I can list all infinite answers that land here on that orange angle by saying it's at 2 pi over 3 plus a full circle more. How many full circles I'm going to add? It doesn't matter. I'm going to say plus 2 pi k, where k is just some interval. So if k is 0, I didn't add any circles. If k is 1, it's adding 1 circle. If k is 10, I'm adding 10 circles and landing right back there. So by saying I've got my answer is 2 pi over 3 plus 2 pi k, that's listing all infinite answers that land on that yellow radian measure. I could do the same thing with my pink one. I could list all infinite angle measures that land on that pink one by saying, hey, it's going to be 4 pi over 3 plus a full circle k times. So plus 2 pi k. Now, if I wanted to be really picky about it, I didn't define what this k was, and so I would probably have to say where k is some integer, right? Indicating that I'm adding and subtracting full circles. Now, that would be an annoying thing to write every single time you put these answers. So when you do your homework, go ahead, just write plus 2 pi k, and I will know you mean that k is just some integer. All right, let's try another one. Period of tangent of x. This may seem unrelated, but it's not. You'll notice when we did period of sine and cosine, we said it had a period of 2 pi, and we added a 2 pi k. Because every time it repeats every 2 pi radians. The period of tangent is pi, and that's going to play a role in my next answer. All right, we're going to solve this equation. Tangent squared of x minus 3 equals 0. Not a problem. Get tangent squared by itself, so tangent squared of x would be 3. Take the square root of both sides. Tangent of x would be plus or minus the square root of 3. Now, the unit circle is still super helpful here. It's a little harder to see where tangent is square root of 3 because, right, tangent is the y over x, so I got to think about which one it would be. For these ones, if you prefer using the table of values, that's fine. I'm going to share that table of values with you so you can see what it looks like. Again, I had mentioned it up here, saying that there's a handout that has both the unit circle and a table of values that can be useful. So I'm going to show that to you, and we're going to find out where tangent is equal to square root of 3, or negative square root of 3. All right, here is that table of values I was talking about. The handout has the exact values for all the common angles from 0 radians all the way to 2 pi radians. If I scroll down, there's the unit circle. But here I was talking about tangent. I wanted to know where tangent was equal to square root of 3. So here's tangent up there. I could say, oh, excuse me, it's equal to square root of 3 at pi over 3 radians. It's equal to negative square root of 3 at 2 pi over 3 radians. Any more? Yep, square root of 3 again at 4 pi over 3. And negative square root of 3 at 5 pi over 3. So they actually have 4 times tangent is equal to square root of 3 or negative square root of 3. And we're going to list those 4 times and talk about how tangent having a period of pi can make my work a little simpler. Okay, so the 4 times that tangent of x was equal to square root of 3 or negative square root of 3 on my unit circle were at pi over 3 radians, 2 pi over 3 radians, 4 pi over 3 radians, and 5 pi over 3 radians. Now, I could write all those answers separately, and that's fine. I could say I've got an answer at pi over 3 radians plus 2 pi k for all the infinite answers that landed on that one. And then I could say x equals 2 pi over 3 radians plus 2 pi k for all the infinite answers that land there. And I could do the same for the other two. All right, there are all of my answers. That is a completely acceptable way of writing the answers. However, remember that tangent has a period of pi. I can cut my work in half because it's kind of annoying to write all those out. The fact that tangent has a period of pi, I can combine some of these answers into a single answer. I can say this a little bit more efficiently by saying x equals pi over 3 radians. And instead of saying plus 2 pi k for a full circle, I could say plus pi k, since tangent has a period of pi. What that does is it takes care of this one, and when I add pi, that's a half of a circle, I'd land there, and it would hit this one. Add another pi, I land there again, add another pi, I land there again, and I can take care of both of those answers in one shot. I can do the same with the other one, x equals 2 pi over 3, which is this one right here. And instead of adding 2 pi k, a full circle, I could add a half circle, and when I add that half circle, my radian measure would land under that red one. So plus pi k, and I've got my answers in a little more efficient route. So either of these is just fine. This is a little more efficient. I'll be writing these answers on keys, but I'll write a little note saying we have equivalent answers right there. The longer ones are equivalent. They both mean the same thing. It's just this one on the right is a little bit more efficient. All right, one last problem. 2 sine squared minus 1 equals 0. All right, I'm going to start this one now. If 2 sine squared of x minus 1 equals 0, then 2 sine squared of x would equal 1, which means sine squared of x equals 1/2, which means sine of x is plus or minus the square root of 1/2, which I don't see on that unit circle, but that's because plus or minus the square root of 1/2 isn't a super proper way of writing radicals, writing square roots. I could keep simplifying this by writing sine of x equals plus or minus the square root of 1 over the square root of 2, right? I can do that with square roots. Square root of 1 is just 1, so this would be plus or minus 1 over the square root of 2. And last but not least, we typically don't like square roots in the denominator, so multiply by the square root of 2 over square root of 2. And I finally get an answer of sine of x equals plus or minus square root of 2 over 2. Sine is the y value again. So y value square root of 2 over 2 right there at pi over 4. And again, right there at 3 pi over 4. And again at 5 pi over 4. And lastly, one more time at 7 pi over 4. Now, again, you can feel free to write all 4 of those answers separately if you prefer. So if you wanted to do that, list them all out and say plus a full circle. So your answers would be pi over 4 plus 2 pi k, 3 pi over 4 plus 2 pi k, 5 pi over 4 plus 2 pi k, and 7 pi over 4 plus 2 pi k. That is just fine. You can write them all out. However, you'll notice that these ones are all evenly spaced. I could save myself a bunch of work and just write my answer in one way. I could say my answer is pi over 4 right here. And then instead of adding a full circle to land back on itself, I'm going to add a quarter of a circle. A quarter of a circle is pi over 2, so plus pi over 2k. A quarter of a circle would land me here onto 3 pi over 4. Another quarter of a circle lands me there onto 5 pi over 4. Another quarter of a circle lands me there, 7 pi over 4, and then another quarter circle brings me back. So having an efficient way, if they're evenly spaced, makes it really nice. I could give my answer in just a single answer like that. Or if you prefer, you can write your answers out, all 4 of them. They both work. Okay. Your assignment is worksheet 5.1a. If you have questions, find me during my office hour. I'd love to talk to you. See you later.